So just to go over a quick recap of what we've been looking at, we're considering the case where we start with some kind of response data and we want to characterize the nonlinear resonances that occur or are captured by that response data. And our procedure is to apply the wavelet-bounded EMD to extract monochromatic IMFs. We then apply the Hilbert transform to extract an instantaneous amplitude, phase, and frequency for each of those IMFs. That then leads into a slow flow analysis where we're asking, are there any slow angles in the response? And we're looking for non-time-like phase and loops in the phase trajectory. If there are, then the averaging theorem fails, and we end up seeing that there is a resonance, a nonlinear resonance in the response, and that allows us to characterize that based on how you constructed that phase variable. If there are no, all of the phase is time-like and there's no loops in the trajectory, then there's no resonance in the response, and that then allows you to eliminate that type of resonance. All right, so we're going to go back down now to our second example. And in this case, we are considering a linear oscillator connected to a nonlinear energy sink. A nonlinear energy sink is a type of broadband vibration absorber. And the key thing here is that it's got no linear stiffness, coupling it to the LO. The NES has very low mass and has a very strong nonlinear stiffness and a weak damping. Actually, the damping on the LO and on the NES here are equivalent, but they're both weak. So equations of motion are shown up there, and we simulate the response here for zero initial conditions except for x dot of 0 is equal to 0.2, and for the time from 0 to 1,000 is non-dimensional with a sampling rate of 10. We're going to, in this case, because there's no linear coupling stiffness, we can't examine the linear natural frequencies to try and identify a particular ratio between them, because one of the natural frequencies will be 0, and so the ratio is just infinite, or 0, meaning that any ratio could occur. Okay, so what we are going to do is we're going to plot the displacement response, wavelet transform, and the maximum wavelet transfer for each mass. We'll then do the decomposition using the wavelet-bounded EMD, and then compute a special phase variable, for in this case for a one-to-one resonance capture between the LO and the NES. All right, so here you can see the displacement response and the wavelet transforms and the NWT spectrum. You can see in the beginning, if we just look at, well, first off, you can see that the NES response is much larger than that of the LO, and the LO dies out relatively quickly, dying out around a time of 300, and the NES dies out a little bit later than that, around a time of around 500. In the beginning of the response, looking at the wavelet transform, the dominant component for the NES, this one right here, is relatively flat, and it's at the same frequency as that for the LO. And then after the LO dies out, we can see that the frequency of the NES then decreases until it hits a 0 frequency as the energy is dissipated. Okay, so for the MWT spectrum, we can kind of see that there is some peaks here, one here, and here. And we are going to use the following characteristic frequencies. We'll say that, we'll just say the characteristic frequencies, which we're going to use in the wavelet-bounded EMD. Characteristic frequencies are 0.225 and 0.16 here. All right, and on the next page, I have the comparison between the response of the LO and its first IMF, and on the right, the response of the NES and its first IMF. I did not include here the second IMFs, or the IMF with the higher frequency here, because we're interested in a one-to-one transfer between these two dominant modes shown here, One thing I will point out, if we look at the instantaneous frequency of IMF1 for the LO, we get this sudden jump here, and then it settles into some constant value. That is due to the signal actually dying out, and then it no longer responding or having a very, very weak amplitude in terms of response. For the NES, you can see that it tracks what we saw previously when we looked at the wavelet transform of the displacements. Okay, and you can see here that the two IMFs are reasonably well separated compared to that component at 0.225. All right, so from here what we're going to do is we're going to construct a special phase variable. We'll say we construct the phase variable and this phase variable will be phi hat 1-1, 1-1, and it's a 1-to-1. So in this case, we are defining the phase variable to be some ratio relationship or a 1-to-1 relationship between the first IMF of, sorry, this should be a 2-1, right? Because it should be the second degree of freedom. So first IMF of the first degree of freedom and the first IMF of the second degree of freedom with a 1-to-1 ratio. We'll say it's a function of time, and then we're going to plot the phase and phase trajectory. Which I have done here. The phi in the y-axis labels and on the left and on the right plot in the x and y, that is wrong. It should be 1-1, 2-1. So, but looking at the phase plot, the variable is defined correctly in the code. It's just a labeling issue. So looking at the phase trajectory or phase plot, you can see that there's a clear non-time-like behavior right here. In fact, we'll label that. This is clearly non-time-like. It starts immediately. And then right around a time of around like 380 or so, we enter into some kind of time-like response. And then looking at the phase trajectory, we start in a capture into this resonance capture, and then we escape over here. And then one thing that I would add here is that we're looking at right here in the beginning. That's where that plot comes from. It's right in the beginning. So indeed, we have this non-time-like behavior, and we have these loops in the phase trajectory, and you can therefore conclude that there is a 1-to-1 energy transfer from the LO into the NES in this case. So you can just say here, based on the two plots above, we conclude that there is a 1-to-1 transient resonance capture between the LO and the NES, where TRC stands for transient resonance capture. Okay, so you can find the code for this on the next page. We're going to go ahead and look at the third example. For the third example, I took these from the paper. You've seen this, you've had access to this paper before, so I don't have any code to share with you. For this example, although it's very similar to what is in the previous two examples. So in this case, we're again considering a linear oscillator with a nonlinear energy sink attached to it. In this case, it's a vibro impact NES, which means that whenever the relative displacement is equal to 1, there is a hard impact occurring in one of these stops here, and we then apply impulse momentum and the standard impact equations and recompute initial conditions and then move from there. Okay, so this is simulated for 0 initial conditions, except for that the LO is given an initial velocity of 5, then it's integrated from 0 to a time of 2,500. Again, this is non-dimensional. You've seen this, where you've seen a similar response. Actually, I think you might have seen the relative displacement signal before for this system. Nevertheless, you can divide the response into four different stages as shown here. And in the top is the displacement, below that is the velocity, and you can also take a look here at the amount of energy that is dissipated by this VI-NES. And you can see that the rate that the energy is dissipated changes at the beginning of each of these stages. One thing I'll add here is that in stage D, the response here actually becomes linear, meaning that there are no longer any impacts occurring in the system. That's the only source of nonlinearity is the impacts. So stage D is when the system becomes linear. Actually, no, that's not true. That's incorrect. It actually becomes linear somewhere around here. And I don't know the exact time. And if we go to the next page, what you'll see is the number of impacts per period. And you can see in stage D, we do have some impacts occurring, so that's why I know I'm wrong about it being linear in stage D. I thought it was, but it's not. What you can see is in stage A, we have about 4 impacts per period. In stage B, there's around 2. In stage C, it switches between 1 and 2 per period. And in stage D, we sometimes have 1 impact. Sometimes we go for a short amount of time without any impacts. Sometimes for a longer time without any impacts. And then I think the time of last impact is right over here, actually. Although I would need to double check to make sure. Okay, so here's the displacement response for each of the NES and the LO again. Beneath that is the wavelet transform. You've certainly seen something that looks like this previously in one of the worksheets. And in stage A, you have a rich frequency content with a bunch of different components. Stage B, you really only have 2 dominant components. And in stage 3, you have some kind of non-regular response with 2, maybe 3 components. And then in stage D, they switch down into only having 2 dominant components at the same frequencies as the linear natural frequencies. Below that is the maximum wavelet transform code, and you can see here that in both signals they're dominated by some kind of component at around 0.15, and then there are a few other ones at higher frequencies as well. And in fact, if you go to the next page, you'll see that we are actually able to decompose and extract out here 6 different IMFs for both the NES and for the LO. Shown on the screen right now is the IMS for the NES, where you can see that just based on the wavelet transform, they're reasonably well separated. Certainly 6 and 5 at the very top there, they actually will have 2 components in them, although one of those components is very weak. And we're interested in studying the lower components anyway, the ones that have the highest amount of energy and the largest response. These are the IMS for the LO, as you can see here. Again, we're getting a good decomposition, a good separation between them, just like we did for the NES. All right, so what we then do is we define a set of difference IMFs, and these are defined as D sub n of t is equal to C sub n of the NES t minus C sub n LO of t. Oops, So in this system, we're interested in understanding the relative displacement because that's when the impacts occur. Whenever that relative displacement is equal to 1, that is when an impact occurs. And so we're interested in studying and understanding the behavior of each of these IMFs or each of these components with respect to being a relative difference or so forth. So what you'll see in figure B here is in black in the background is the relative displacement between the NES and the yellow, and then superimposed on top of that is one of these different IMFs, with the red being the first difference IMF. That means using the first IMF or the first NNM. The blue then is the second difference IMF, and the green is the third difference IMF. Okay, so to study internal resonances in this system, we're going to define the following phase variable. In this case, we've dropped the degrees of freedom in terms of the subscripts, and so the I and J only correspond to the IMFs, and then M to N is still going to be the ratio. And so this is defined as M times theta I hat the LO of T minus N times theta hat sub J of the NES of T, and here I and J are equal to 1, comma dot 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 up to 6, and M and N correspond to or live in the space of positive integers. Okay, so the phase variable is the opposite of the difference IMFs, where we had the NES in the beginning and subtracting off the IMF, well, having the IMF of the NES, subtracting the IMF of the LO. However, the phase variable that we're showing here is identical to what you would define if you used the phase of the NES first, meaning that if you had the phase of the NES minus the phase of the LO, this variable is going to be identical to that. If anything, it'll just have a different sign somewhere. Okay, so we're going to look at 3 different cases. The first will be what we'll define as phi 1, 2, 2 to 1 of T. So this is a 2 to 1 transient resonance capture between the first IMF of the LO and the second IMF of the NES. Meaning that energy is being transferred and exchanged between the LO and the NES through the first NNM of the LO and the second NNM of the NES. The second case we're going to look at is a 3 to 1, where we'll have phi sub 1, 3, and 3 to 1 of T. And so in this case, the first IMF is exchanging, although this tends to be a reversible, it's really pumping energy into the third IMF, or the third component of the NES. And then the last case we're going to look at is phi 2, 2, and this will be a 1 to 1. So we're looking at a transient resonance capture between the second IMF of the LO and the second IMF of the NES. Okay, so what I'm showing here is that case A, which was our 2 to 1 transient resonance capture from the first IMF of the LO to the second IMF of the NES. You can see the phase variable shown here, and we have several different periods of slow or non-time-like phase. This has been split up into subregions with lowercase Roman numerals. I is in the beginning, and then the other 3 occur in stage 3. And you can see in the phase trajectory, we end up having these loops. We have to zoom in quite a bit, and if you look at the 4 subplots, you again see we have these loops indicating the presence of transient resonance captures. And so indeed, that phase or that type of nonlinear resonance does occur, and it occurs actually 4 different times in the response, as shown here. If we take a look at case B here, which was that 3 to 1 transient resonance capture between the first IMF of the yellow and the third IMF of the NES. Again, you'll see here that there are periods of slow phase or non-time-like behavior, and loops do appear in the phase trajectories as well. In these cases, you don't have to zoom in as much to see them on the right, but still in the bottom 4 subplots, you can see that we have zoomed in on them. Okay, take one look at case C here, and this is the one-to-one transfer between the second IMF of the yellow and the second IMF of the NES. And again here you can see that there are at least 4 different transient resonance captures that occur. There are 3 different ones that occur in stage A, and then there's one that occurs in both stage D and stage E. Although I suppose that should actually be stage, should be B, C, and then this is D. All right, and that